Hello and welcome everybody to Solidworks Live. We're excited to have you all here today. We have a great topic. I've got everybody in the chat here. So again, this month we're going to be trying to engage with the chat. So if you have questions as we go along and we're discussing design for additive manufacturing, make sure you post those questions in the chat. I see here on YouTube. Hey Ray, great to see you. Nav Simran, welcome from Australia. Jeff Setzer, glad to have you here. Last month, we had a really exciting topic. We talked about CNC machining with our Delmia suite of tools, something traditionally called subtractive manufacturing, where we're taking material and removing material to create final products. This month, I wanted to bring a special guest on. We had a lot of comments. People wanted to learn more about 3D printing. I thought, let's go to the next level. Let's bring on an expert and talk about additive manufacturing. So we're going to kind of elevate that conversation of 3D printing a little bit further. And to do this, I have a special guest joining us here today, Paul DeWys from Forerunner 3D Printing and DeWys Engineering. Paul, welcome to SolidWorks Live.
Hey everybody, thank you for having me on. Hopefully we can have some fun talking about additive and design for additive today.
Yeah, so Paul, tell us a little bit about who you are and what your organization is so people kind of have an understanding of your knowledge of this topic.
Yeah, so I've been a long time SolidWorks user and actually even pre-SolidWorks back in college. I was running a CATIA when I was in school and was the lab monitor for CATIA lab. And pretty much started with a bunch of kids were paying me to do their CATIA homework. And then I wondered if companies would pay me to do their CATIA work. And then by the time I graduated in 2010, I'd built up a really, really small customer base. And I thought, hey, you know what, let's take the summer and see if I can turn this into a real business. And so over the course of 2010, got out in the real world and realized that CATIA doesn't have a massive install base, but everyone was using SolidWorks. It was every company I went into. They're like, oh, do you do SolidWorks? And I'm like, no, we do CATIA. They're like, oh, we need a SolidWorks guy. So by the end of that summer, I had purchased a seat of SolidWorks and gotten plugged into the SolidWorks community and been a huge SolidWorks fan ever since. And so built our company really on the SolidWorks platform. And from 2010 to 2016, built up our engineering business. We do pretty much anything, but our real specialty is automation and machine design with a little bit of product development and then a bunch of other random stuff mixed in there as well. And the whole time I was really watching the rise of the consumer, regular people hearing and seeing 3D printers for the first time because like the rise of MakerBot. And I was like, man, there is an opportunity to bring this to the world of machine build and automation. But there really wasn't anyone that could bridge that gap who knew additive and knew machine design. And I thought, you know what, that could be us. So through a kind of a weird series of events in 2016, I purchased the assets of a legacy 3D printing company, the next city over from us, moved that equipment into our facility, and we just started learning on the job. And so that's where our Forerunner 3D printing business unit came from. So since then we've grown, added a lot of new technologies. And, like I said, our real claim to fame is we are experts in not only additive manufacturing, but especially design for additive manufacturing. And that's what I'm here to talk to you lovely people about today.
All right. Well, that's great, Paul. So we're still kind of in these weird times right now. So you had the opportunity to give me a virtual tour of your facility and kind of show me what some of your capabilities were. Let's go ahead and let's share with the audience that same virtual tour so they can kind of see what you're doing at Forerunner 3D Printing.
This is just a wide swath of a bunch of different things that we do. About half of what we do is end-use parts. The other half of what we do is prototypes. So I'm going to take you in the MJF room and show you one of our workhorses in here. So this is HP MJF. It is a nylon 3D printer. It can also print in TPU rubber, and it prints with a powder bed method. So if you want to take a look in here, you can actually see tonight's build running on the machine. We're printing some prototype parts for one customer and then some end-use parts for one of our machine builders fixtures. So this is the printer, and then as you walk out, you'll see the post-processing equipment that actually does all the powder handling and unpacking. So now we're kind of getting into our SLA lab. So upstairs, the MJF machine is much more end-use parts, low-volume production, bits and pieces for our machine build clients. This is where mostly prototyping takes place. So, like for example, in this room right here, this is actually our model making room. So we've got a model maker who works at on the Forerunner side of the business, and he'll come in here, sand parts, paint, do different things like that to build up really nice prototypes and trade show models for our customer. But if you come in here, we'll look at some other machines. So these are our SLA machines. This is an SLA 5000. This is an SLA 500. Basically, this one prints in a white ABS material, like ABS material. This one prints in a clear ABS-like material. And so we use these to print a lot of different prototypes and things to check out parts before they go off for tooling. So for example, steering wheel component, you want to make sure all of your screw bosses and clips fit. That's what happens in this room. We print a lot of this type of stuff, as well as things like I was saying, trade show models. So, you know, this is a product that we developed upstairs. One of my designers designed this whole product. We worked with one of our electrical engineering partners to outfit it with all the electronics. And then we printed up an enclosure and we made it look really nice for our customers' trade show booth so they could go show it off at shows and show it to buyers. So that's kind of the complete life cycle here at DeWys Engineering and Forerunner 3D printing. Start with laser scanning, go into design, and take it all the way through additive and give the customer a physical product that they can actually put their hands on.
Paul, that's pretty exciting, all the different technology that you have available over at Forerunner 3D Printing. We actually have some comments coming in from chat, which I think we're actually going to answer. There's on LinkedIn, we have somebody asking, they asked about like stereolithography. Would you use those for prototype prints? And then there's some questions on YouTube as well, asking us about printing also. So I think what I want to do is I had some questions for you that I think will answer some of these. And I want to start right away, Paul, talking about there's 3D printing, and then we're talking about additive manufacturing. Why the different language, Paul? What do we mean when we talk additive manufacturing?
Yeah, so I think anyone you ask in the 3D printing or additive industry might have a slightly different answer here. But my answer to this would be, we started out back in the late 80s and early 90s with rapid prototyping, because that's what it was. You were prototyping parts. And I think, around that like kind of 2008, 2010 timeframe when MakerBot really started to come onto the scene and the general public started to hear about this for the first time, I think a lot of media companies out there really kind of popularized the term 3D printing. And it's true, we do 3D print. That's absolutely what we do. But really, the industry as a whole is really moving beyond rapid prototyping or printing, simple one-off, toys and things like that. We're moving into true manufacturing, serial manufacturing. Anywhere from 10 parts to 10,000 parts. There's whole companies like Smile Direct or Invisalign. Their entire businesses are built on additive manufacturing. They're making tens of thousands of parts a day using 3D printing. So I think additive is just kind of a way to kind of show that the industry is moving beyond where it's at today into a more true manufacturing type of business.
All right. Well, let's take a look at some of the technology that's available. What we want to do now, Paul, is we want to look at different forms of 3D printing or additive manufacturing and what some of their pros and cons are. And you have a lot of these technologies available in-house. So we're going to talk about 3 different printing technologies, and we're going to take a look at some examples of where you've used the different. Let's start with probably, I would think, the most common one that engineers understand, and that's going to be SLA or stereolithography. Can you explain what SLA is and how it works?
Sure. So SLA is the great granddad of 3D printing. This is what Chuck Hall at 3D Systems commercialized in like 1989, 1990. And it's really where 3D printing began. So what you see here is we've got a vat full of a photopolymer, and we have a laser beam that's filtered to be a UV laser beam. Anywhere where that laser beam touches the surface of this vat, it is going to instantly harden that material because the UV light interacts and causes a chemical reaction in that liquid to harden and to glue itself essentially to the layer below or bond to the layer below. So you can see here an example of like that layer by layer construction, and you'll notice there's support underneath it. There's a mesh. It looks like in this kind of like a mesh underneath of it. That's support material. With SLA, you can't just have your part sitting in the vat. It would move all over the place and it wouldn't print. So that support material is there to anchor the part in position. And then when you're done, it's breakaway. So you just tear it away and you're left with your part and you throw your support away when you're done. And so, yeah, so that is SLA or stereolithography in a nutshell.
Okay. So interesting question just came up it was on LinkedIn here. So there's so much chat going on. I'm trying to get back to the question here. It's from Naga Gopal, asks on LinkedIn, what kind of materials can we use for 3D printing? And this is something that's, you can probably clarify, it's different for each type of process you use, right?
Yeah. So with this, it's a liquid resin. So, with an SLA, it's not like it's a liquid vat of ABS. It doesn't work that way. It has to be a photopolymer. It has to be UV reactive. So a lot of times what people do is they tune photopolymers to try and have the mechanical properties of something like ABS or polycarb or something like that. And so if you go on to, either DSM or 3D Systems websites, you'll see tons of different SLA materials, or even like Formlabs too. They've got all kinds of different SLA resins that do all kinds of different things. And that goes for FDM and that goes for MJF, which we're going to both talk about those here in a second.
Well, you bring up, first of all, let's look at some design examples where you've used SLA in your design process here. So let's talk about this first design, and let's talk about why you chose, what the product is, and why you chose to use SLA in this specific example.
Yes, so this is a part off of a piece of industrial equipment, factory automation. And what it does is it blows dust off of a part as it's run across it, and also has vacuum channels to the left and the right to suck that dust up. And the customer had a couple requirements. They had very specific geometries for the blow-off portion, as well as very specific geometries for the vacuum in order to get the effect that they were looking for. And it was really important for them to be able to see inside of the part, which means it needs to be clear. Well, we have a really good, high quality, clear SLA resin. It's called Somos Watershed, and so that material was clear. The SLA gives us the fine feature detail to do all the holes and stuff we'll see here in a second. And then when it was done, we actually, all the way on the right, we actually insert the SLA block into a stainless steel shoe. Because the SLA material is not really that great in rough environments. It'll crack, it'll yellow from UV overexposure. It's not great in high heat. So that stainless steel shell protects the kind of fragile SLA, which has all of our fluid paths and air paths through it.
So what's interesting about this, Paul, is we're actually, sorry, there is so much chat coming in today here, Paul. I'm like trying to watch the chat and pay attention to what you have going on. Really quick, I'm gonna throw a couple questions out at you because I don't want them to get forgotten.
Yep.
And I know we're gonna touch on some of these as we move on. There was, again, on LinkedIn, it said, how is modern 3D printing adapted to newer technologies like generative design? Tried printing a model created through this, the same using STA UV resin, but it didn't turn out quite as expected. Like, are you looking at any of these technologies and what you're doing, Paul, like generative type design and then printing that type of geometry out?
Generative is definitely on the horizon for us. Right now, we really don't have a lot of demand from our customers for it. So, it is an expensive product. And so, for that reason, we haven't really jumped on the generative thing yet. I've gotten the trial version from Solidworks, and we've used it a couple times, and it's really cool stuff. And I think that just like anything, it'll become more and more useful the more it gets developed. And I think that it will definitely have its place going forward. the viewer's question, if you were trying to use generative design and you were trying to print it on an SLA machine, you probably ran into an issue with having a ton of support structures inside of your elements of your generative design. Maybe that's what they're referring to by it not kind of turning out the way they thought. Honestly, if you're doing generative, you really want to look at SLS or MJF. You want to look at powder bed systems, or maybe Polyjet, but Polyjet's not going to really give you the strength that you're probably looking for. So I think that with generative, you really want to look at the powder-based systems because there's no support, and we're going to talk a lot about that in a minute.
Yeah, so that's another question here. It came up, it asked, what are some of the design parameters that I need to consider when thinking about designing for 3D printing or additive manufacturing? And I think this part is good. I was trying to like absorb all these questions, and one of the things we discussed earlier on is this design. Now there's some unique geometry in this design. Not only is this part a non-machinable part, right? You have cavities inside of the part where no tooling can get inside of there. But you mentioned something about the geometry on the left side of the view. If we pull that back up, we can see that you have some very unique geometry that you're moving this air through. Can you explain some of the design characteristics that went into this?
Yeah, so if you look at the left-hand side of the slide here, there's that red section cut through the middle of the detail. And you'll notice that in the center, we have an arch, and that is our pressure chamber. That's where we're blowing air through that array of holes across the top of it. And then off to the sides, you'll see there are some 45, or actually probably more like 60-degree angles going up to our vacuum mouths. And those are vacuum chambers. And so if you can do an arch is a self-supporting structure. So think about like bridges back in the Roman days, right? They always did them as an arch because it was self-supporting. Same thing here. You don't have to print supports inside of there. And then the vacuum vaults on either side have that 60-degree angle. Anything over 45 degrees is a self-supporting structure. So you don't have to have supports printed inside of there. And because this is a single piece, you couldn't ever get the supports back out from inside of there once you printed it. So it's very important in a situation like this, not only to have self-supporting geometry, but also, since we're printing in a liquid resin, you can drain the resin back out again, flood it with isopropyl alcohol, shake it real good, wash out those interior chambers, and you're left with a perfectly functional part that you can blow air through, you can vacuum materials through it, and you don't have any support structure left on the inside for everything to get hung up on.
All right, so that's pretty cool. We got a lot to cover. So I'm sorry we can't answer all the questions in chat. Paul, you are getting probably the most questions I've ever seen come through in chat.
I will say, guys, if you go to forerunner3d.com, you can find me on there. I'm happy to take emails, or I'm very prolific on LinkedIn. So Paul DeWys on LinkedIn, send me an invite and we can chat.
Yeah, we'll try to answer a few questions for each part of the presentation here. It's literally it's blowing up on all the social media right now. So let's look at your next manufacturing process you use for additive, and that's FDM. Can you explain to the audience what FDM is? So we talked about SLA. What is FDM?
So FDM is fused deposition modeling. When the general public thinks of 3D printing, they think of FDM. To put it crudely, it's a CNC controlled hot glue gun. Basically, you've got one or two extruders sitting next to each other, and one of them is doing a support material. The other one is going to be doing a build material. And so the build material might be ABS, could be polycarb, could be like an Altem or PEEK. And then your support material is usually a water-soluble material that can be soaked away essentially after the printing. So here we have to print with supports, just like we saw with the SLA machine. You can see that kind of beige colored material under those layers. That would be your support material. But that, unlike the SLA where you have to tear it away, here you can soak it in a chemical and it will actually dissolve away over time. And so that does do some cool things for being able to do washout support structures inside of parts. I will say that SLA part I just showed you wouldn't be good with FDM because you need agitation to go along with it, and trying to get agitation inside of vault structures is difficult. So It doesn't really do good with trapped volumes, especially small trap volumes. But big, broad parts like this, I mean, no problem. That support structure will wash right away. But yeah, the general public, they think of a MakerBot, they think of a RepRap, they think of Ultimaker, they think of an Ender. You know, you can go on Amazon, you can type in FDM. Actually, if you go on Amazon and just type in 3D printer, I'd be willing to bet all the money in my wallet right now that the first thing that pops up is probably an FDM machine. Although these days it could be SLA. So Jeremy, maybe I'm going to have to buy you lunch if you check me here. But the general public, they equate additive manufacturing, 3D printing, they equate that with FDM because it's just so prevalent in schools. And I mean, even like our local library, like I live in a little town in Western Michigan, and like our local library was like, we got a 3D printer now. And I'm like, this is crazy. Like these machines are just all over the place.
Yeah. And cost-wise, FDM, like we haven't talked about that. FDM from a consumer level, it's fairly a fairly inexpensive process, right?
Yeah, I mean, you can get a 1 pound roll of filament for like $25, and you can print a lot of parts with one roll of filament. So yeah, and I mean, the machines themselves can be had for a couple $100. So I mean, you can get into the 3D printing game well under $1,000 with a FDM printer.
And just for comparison here, let's go back. Let's talk about SLAs. One of the cons we didn't talk about, that resin you use in an SLA machine, is that stuff inexpensive?
I would argue it might be the most expensive liquid on planet Earth. So if I were to buy I think it's a 20 kg bottle, or maybe it's even a 10 kg. It's like $2,000 a bottle. So to fill a vat on a machine like we were looking at is like 75 grand.
Wow. All right, so let's look at some examples of where FDM makes sense, and let's look at a design project you guys looked at. Tell us a little bit about this tape applicator hand tool. And first, why did you design this? What's it used for? Yep. And then let's look at why FDM.
So one of our big customers is a very, very large international tape manufacturing company. Side note, you would not believe the amount of things that are just held together with double-sided sticky tape. It's kind of terrifying. Anyways, one of their big customers, actually a couple of their big customers, are window manufacturers. So all the window manufacturers that you know of basically use this product. And a lot of double hung windows, especially the lower quantity ones, are assembled by hand down in Mexico. And so they were just getting eaten alive on CNC costs because they have a very wide range of window profiles. So they need a very wide range of these hand tools, but they might only need 2 or 3 of each of these hand tools. So it was a low volume, but a high mix. And so in that case, CNC really struggles to be cost effective in something like that. Whereas with additive, we can do really well in situations like that. So what we did is we redesigned these applicators to be very FDM friendly. And the reason we did FDM over like the SLA, remember I told you SLA is fragile, doesn't do well in high heat. It will yellow from UV overexposure. Here, we're not printing in something like ABS. We are printing in ABS. So it's rugged, it's strong, it's cost effective. And you can, as long as you design your parts and not like these, we figured out how to design them with no support. So there's literally no support needed for these. So we literally print them, rip them off the print bed, throw them in a bag, ship them to the customer. It was the lowest cost option that we could come up with, but it was important for us to design it for additive because we could eliminate so much secondary work from having to deal with supports.
All right. Well, Paul, we have a whole bunch of questions here. So I'm going to jump back to chat. Yep. We'll jump on to the next project. I wanted to ask this question right now while we were talking about FDM. Rumel Sujan on Facebook asks, is it possible to use steel in 3D printing?
Yes. Yes, it is. So metal printing is definitely a thing. It's actually a big business. But it is eye-wateringly expensive. So the companies that routinely use stuff like that, SpaceX has a huge additive department. Boeing, Lockheed Martin, huge users of metal additive. Med device companies, metal additive. And if you'll notice the trend here, it's all products that have ridiculously high margin, where if they can increase the performance by a couple percentage points, that is of a lot of value to them. Versus, like for example, my machine build customers, it's very, very hard to justify the cost of a metal printed component because there just isn't a huge value add there for it yet. I really think in the next 10 years, you're going to see metal printing machines get to where polymers are at today, and it's going to be the Wild West. But for right now, metal printing is very limited to really high-end applications. It's getting every year, it's getting cheaper and cheaper, but right now it's still fairly unattainable for most projects.
Yep. And there's even technologies out there now where they're printing with carbon fiber inside of there. One of our partners, Mark Forged, great piece of equipment. Another question for you here. This is interesting. I'm throwing you under the bus here. Scott O'Connor on LinkedIn asks, is there a strengthening coating or spray that you can use on your printed parts after printing to strengthen the material? And I'm sure that differs depending on the printing process you use.
Yeah, so there's a couple vapor smoothing technologies out there that use like it's not really acetone, but it's like an acetone cloud to remelt the surface of parts. And I have seen some preliminary stuff to show that does increase your X, Y, and especially your Z strength. As far as like anything that you could get at home, I will say this, be very careful using acetone at home, especially if you're vaporizing it. You can kill yourself very easily. So I would recommend not doing it. But acetone vapor smoothing can help. As far as like coatings go, we haven't really seen a coating that you could put onto a part that would dramatically increase its strength. We do a lot of work with Cerakote. But that's more for color and wear resistant color on parts. I wouldn't really say that it makes the parts much stronger than what you'd get directly off the machine.
All right. And the last one here is just a comment. It's going to lead us into our next section. We have one more project in the FDM realm to look at, but Jeff Setzer says one of the night, and I don't want to miss this because this is important. Let's remember it's Earth Day today. One of the nice things about MJF is that about 80% of the unused powder can be reused, right?
He's absolutely correct.
About that Yeah, we're going to talk about that technology in just a little bit. I want to take a look at another FDM project you use because animals, especially dogs, hold a special place to me. So tell me about this project here.
Yeah, so we do a lot of business with a couple of veterinary clinics and some animal research firms. And sometimes they need to put a animal, in this case, a dog, into an MRI machine. And anyone who has a dog knows that if your dog is laying there asleep, they're not really that still when they're asleep. There's things moving. There's always something happening in their heads, even when they're asleep. Obviously, if you're doing an MRI, you need them to be very, very still. And so also with an MRI, you can't have metal in the machine at all. It will be a disaster. So everything has to be plastic inside that magnetic field. So one of our customers came to us and said, we have this surgical brace that we really like for working on animals when they come in, but it's titanium. We can't put it in an MRI machine. And so they said, could you make us a plastic version of this? And so we said, yeah, absolutely. So this MRI fixture is all plastic, all printed. It's a combination of FDM and MJF parts. And even the green fasteners that you see, those are all plastic thumb screws from McMaster. So there is not any metal in this at all. So they can set this. They can fixture the animal in this fixture and put them in the MRI machine. And then if they have a little dream where they're chasing a rabbit, they're not going to throw off the MRI scan.
Very cool. So these are some good examples here where FDM makes a lot of sense.
Yeah, absolutely.
Now I want to talk about what the conversation I had with you last week over the phone is arguably probably your favorite technology, or maybe I misunderstood that. No. You seem very excited about this technology, MJF.
Yeah, so MJF's the newest technology that we've added in the last 2.5 years at this point. And it's a relatively speaking, brand new technology. I think it got commercialized in 2016 or maybe early 2017 from the good people at Hewlett Packard. If you go to Best Buy and you pick up a paper printer, same people that make that are the same people that make this. And so it's a powder bed machine. So we spread a layer of nylon, which you just saw, Then we spray a black fusing agent onto that white nylon powder, and we spray a detailing agent around the edges to give us a thermal barrier. And then we hit it with high intensity IR light. And that high intensity IR light, it's absorbed by the blackened regions, but it's reflected by the white powder that's around it. The blackened area goes above the melting temperature of the nylon and it sinters. Whereas the white powder around the rest of the part, it does not sinter because it does not get above its melting point. So you can see here, layer by layer, 3,000ths of a layer of an inch at a time, we're building these parts. This technology is really cool because it's fast, it's economical, and it makes incredibly good end-use parts. And our machine build customers absolutely love it. And we've actually beginning last year, started a lot of low-volume production projects with it as well for end-use parts that are actually out for sale in the world today.
So what's one of the biggest advantages of MJF? Like when I look at it, you talked about cost and speed. All the other processes you talked about, you have like this, you have to take into consideration how you're going to get rid of the support structure. What's it look like with an MJF machine?
That's the best part. There is no support structure. So you notice there's powder underneath the part. You can see it right here. You don't see any support underneath the part because there isn't. It's just every time it lays down a full layer of powder. So if I have if I'm building a wall like this, and then all of a sudden I have a 90-degree coming out like this, normally I would have to build support structures right here. In this case, this whole area is already full of powder, unsintered powder. So I just keep building on top of that unsintered powder, and our part just builds. We don't have any support. So when we're done, you'll see a video in a little bit. We literally just vacuum up the excess powder, which we can reuse 80% of that powder on the next build. It's a really, really economical machine, and it makes incredible parts.
All right. I'm just kind of looking over the chat here really quick. Paul, I'm going to keep going right here. You know, there's a lot of like speculation. I'll ask you this question, Paul.
Sure. Please.
It's a lot of speculative stuff. Do you see additive manufacturing ever replacing either CNC subtractive manufacturing or plastic injection molding? And I know you have a strong opinion on this, so that's why I wanted to ask you this question.
No. Look, I love my equipment manufacturers, but they've done a huge disservice for our industry by going out there and saying we're going to displace injection, we're going to obsolete injection mold presses, we're going to upend the machining industry. It's not the case. This is another tool in your toolbox. It's like, you wouldn't grab a sledgehammer to put in a screw. You'd grab a screwdriver. Okay. And I could go on an hours-long diatribe about this, but I'm going to leave it to this to say, in our lifetimes, no way. Maybe in some far-flung future on Mars, maybe, but I don't see it, and you don't want it anyways. Those other technologies, they have so many strengths that complement additive in different ways. Where things get really fun is when you start combining them. Take a 3D printed part and machine it, or take an injection molded part and bond a 3D printed component onto it with a feature that wouldn't be moldable. That's where things get really exciting.
Very cool. Let's take a look at some examples that you've worked on with MJF, and let's talk about why you chose MJF for these processes. Let's talk about this first one here, the ratchet safety cover.
Yep. So this was for one of our automation customers. They use high-speed torque sensing ratchets when they're assembling, like, for example, putting the lug nuts on your car wheel at the assembly plant, or bolting things into the engine compartment. And these are pretty high torque wrenches, and they're electrically driven. So if someone were to make the mistake of grabbing one of these ratchets while it was spinning, they might have an injury to their hand. So what the customer was doing is they were putting these essentially clutch covers over top of them. So this yellow component, you would grab it and the socket would continue to spin, but the clutch would stop, and so you wouldn't have a risk or a lower risk of an injury. But the issue was, again, kind of like back to that tape thing I was talking about. It was low volume, high mix. So, they need one of these covers for every ratchet that they're going to be using on this line. And they needed something that they could, not have to set up CNC equipment, and not have to, you know, program every single time. So what we did is we redesigned them for additive. Now we originally just printed the design that they had, and the issue is our nylon doesn't have quite the same flexibility or elongation at break that a Delrin has. And so we would actually split these when we would go to press them together. So what we did is we created like a rosebud kind of design. So instead of having a solid detent all the way around, we put it on these petals so that as you push the socket in, it petals open and then snaps back shut again. Another thing that's really cool is we can print the socket size on the outside. This would be something that would be very costly to do with CNC. But here, if there's one thing that people remember from today, and it's the only thing they remember, it's that with additive manufacturing, size will cost you, but complexity is free. So text, texture, crazy features, non-machinable features, non-moldable features, they don't cost you anything extra. It's when you try and go, oh, I want to print the entire door to a car. That is going to be very expensive. But for little guys like these, I mean, they're only this tall. Put as much complexity in as you want, because you're going to be ordering, you know, 50 of them. Each one is going to be different from the next. It doesn't cost you any extra for that complexity.
All right, Paul, I have a comment. Angela Chow on LinkedIn says, totally agree with you on combining the technologies. I think that's awesome. Look at new ways that you can leverage the technology available to you. Last month, we talked about CNC machining. We're talking about additive today. I'm sure we're going to be talking about plastics down the road and some of the things we can do with that. Somebody else said, there was another comment I wanted to see here. It's just somebody else. Cody Gross on YouTube said, you can't beat injection molding for high volume parts, unfortunately.
Nope. And that's the biggest disservice that a lot of the 3D OEMs did, is they came in and they tried to say, oh, our technology can displace those machines. Yeah, I mean, we can displace the low volume guys, maybe, where it's like the 1,000 to 5,000, maybe up into 10,000. But when you get over 10,000, I mean, you better have a really good reason for 3D printing and not just going and building it. I mean, you can go to so many quick turn mold shops. They could build you an aluminum tool. I mean, me personally, I have another company with some buddies, and we commercialize products that we develop. And we just transitioned one from MJF production. We're cutting a mold right now because our volumes have gotten high enough where we're like, we can get so much more margin going to injection molding versus printing these.
Very cool. And then this is a good question about MJF. It comes from Nizar Doshi on YouTube. He asks a question: if there's a hollow part, how would you remove the unused powder without changing the design? And I think your point was you designed for that specific process, right, Paul?
Yep. So you'll notice, like, like that initial SLA part I showed you with all the internal pathways, we've done parts like that with MJF. We have to design in a very well thought out depowdering strategy. And it can be done. We've depowdered some monstrous end of arm tools with tons and tons of long internal airlines and things like that. But there's a real trick and a real art to designing to do that. But also we have customers where we actually will leave powder trapped inside of their parts because they don't care if there's powder inside of it. It's not a weight issue. By leaving that powder trapped inside of there, we get a little bit of structure off of it, and also we don't have the added expense of trying to figure out how to get that powder out.
All right, Cody, I apologize. I don't know why I put the invisible R in there. Sorry about that, Cody, with the last name. We want to keep moving here. We got a bunch of stuff to cover yet. So my background prior to coming and working for Solidworks, I worked for a machine design company here in West Michigan. And a lot of things we did was holding on to parts, using pulling vacuums and things like this. So this jumped out at me as like a very recognizable part. And when we look at the next slide, how you utilize the printing technology blew my mind. Like, if I could have done this, oh man, that was 17, 20 years ago. I used to do that. So let's talk about this part.
Yeah, I mean, it didn't take long when we got our first 3D printer for my machine designers to come walking into my office and go, "Hey man, I got this idea." And that's where most things start around is here. "Hey man, what if we," and then ... And so in this case, we had a machine we were designing, and we were doing a high-speed move to pick and grab a component and move it. And what we'd run into in the past is the airlines would sometimes actually get hung up inside of the machine and get ripped right off the end of arm. And then you lose vacuum and you drop parts and it's a big deal and everyone's mad. So we said, hey, let's actually print these airlines inside of the part. So looking at this slide right here, you can actually see a cutaway in SolidWorks. These gripper fingers, they're printed out of nylon 12. And the beautiful thing about MJF is these parts are airtight and vacuum tight coming directly off the printer. So unlike SLS or FDM, where you're going to have to do some kind of sealing process with like a super glue, essentially, here they're 100% dense right off the machine, no leaks. So we just drew in a freaking, swept path right through the part, and we just cut in the airline, and then we used the hole wizard to put in our fitting holes and put in the hole for the little barbed fitting for the cup, and there you go, you're done.
Very cool. So you were talking about an end-of-line product that you guys, we're going to look at a lot more of these machine fixture things in a little bit. So Paul, I kind of want to jump to the next one. I'm just kind of watching the time here.
Yep.
You were talking about an end-of-life product that you and some partners worked on. This is that product, right? The light case?
Yeah, the light case. So this is one of our products that we've been kind of toying around with for the last couple of years. One of my buddies has one of the Google Pixel phones, I think, and that's the case you see on the left here. And it pretty much started with, he just wanted a cool cell phone case that would hold 3 credit cards because he hates wallets and he hates money clips. He wants everything on his phone. So anyways, I go, okay, well, let's see if there's something here. So we spent a couple Saturdays and ran a bunch of prototypes, and eventually we landed on this case design that you see on the left there. And what's really cool is if you look at the image kind of on the right, you can actually see the fingers through the back of the case. And if you take a credit card, you can fit 3 credit cards in it, and you just slide them in, and those fingers will flex back. Your card slides in, and then the fingers flex back around it, and they actually lock your card stack in there. And then there's just a hole in the face that you use your thumb just to slide those cards back out again. And so we thought that was pretty cool, but the economics just didn't work on these bigger phones. We couldn't get the case to a point where it was really a sellable design on something like Amazon. But then we looked at like a light phone, and a light phone is a very kind of niche feature phone, but they're super popular with kind of like the minimalist crowd. And we thought, hey, wouldn't it be cool to combine a card carrying backpack with a case for your light phone? And so we came up with the light case. And so you can see the kind of the 3 images of, the phone is laying face down, but the backpack is laying facing up. And you can see the different, progressions of using my Topgolf card there. Feel free to steal my identity at Topgolf. So
look at this.
So now you can see, this is back to the other case, but you can see a cutaway. You can see those fingers inside of there. And it's the same for both cases. Those fingers flex out of the way as you load your cards in and take your cards out. And the nylon is durable enough to act as a case for your phone, but also flexible enough where that living hinge feature or snap feature works for holding your cards in.
Yeah, so these are some really cool examples of where you would use this MJF technology. There's a ton of chat going on right here. I just kind of want to look at something here. Dallas Salad says on YouTube, compliant mechanisms in 3D printing are grossly underutilized. True or false?
Totally agree. We have done so much with this for our customers, designing really, really cool snap features and things like that. That they couldn't really manufacture any other way. So yeah, he's totally right.
And then there's a really great question. We've kind of talked about these 3 specific printing techniques. So this brings up a really interesting question. It comes from, I'm going to pronounce this name wrong. I apologize. Dumenku Andre on YouTube says, what is the smallest resolution at which a 3D printer can print? And what technology would you recommend for different things? I think we kind of discussed the technologies, but let's talk about, that's like a pro and a con about everything we've looked at here today, right? Is the resolution at which we can print?
So I've seen some really, really cool stuff coming out of some R&D labs out on the East Coast. The name of the company is escaping me. It's like sub-ohm or something. It's a really, really, really fine detail. I think it's a DLP printer. And I think Empire Group is running them, if memory serves correct. And they are printing stuff that I cannot even believe is possible with a 3D printer. I mean, I'm talking microfluidics, just crazy, crazy small stuff that I would have never thought would be possible. But then you go the other direction and you look at like Cincinnati, the machinery manufacturer, their BAM technology, which is big area additive manufacturing, or Thermwood. They've got gantry style printers that they're printing boat hulls and wind turbine tooling with. And back to our combining technologies, they have swappable heads. So they'll do a bulk additive head, and the part looks terrible. It looks, I mean, they're extruding, 1/4-inch layers of thermoplastic, but then they swap heads and they come back with a high-speed milling head, and then they 3D contour the entire thing. And it's incredible. I mean, aerospace tooling has been and is being radically transformed by these big printers for exactly that kind of use case.
So last month when we had Mike Buckley and John Milbury on to talk about the Delmia technology, near the end of that stream, if you go back into our SolidWorks Live playlist, if you're viewing at home, Mike Buckley actually talked about this, where Delmia is able to program robotics to do additive on kind of this large scale, and then also use Delmia to surface finish all of that out. Exactly what you're talking. He was specifically talking about wind turbine technology there.
Yep.
Very cool stuff. So.
Yep.
Let's jump forward. So I want to get to, let's go through this next part, Paul, a little bit quicker. Some of the features you use inside of SolidWorks. And I really wanted to talk about the technology here. So let's talk about some of the design tools you use in SolidWorks and just a couple of your favorites here. Let's talk about this first one.
3D texture. It used to be people would come to us and say, I want texture on my parts. And I would go, great. Go hire someone that runs a competing package that's good at that, because that's not us. That's not what we do. But when this feature came out in 2019, it was like, oh my gosh, we can actually apply textures, and even a bunch of meathead mechanical engineers like me and my guys can do this type of thing. It's a very, very handy tool, very easy to use. There's some great YouTube tutorials out there for how to use it. The first time can be a little confusing, but just go on YouTube. There's some great people out there showing how to use this tool.
Very cool. Yeah, and if you go back, you can actually watch, there's some videos on the SolidWorks YouTube channel of how this is used. Really cool. All you need is this grayscale image, and you can find these all over the internet, and you can create all sorts of different textures on your material. I think this would be a great live design episode. Paul, if you haven't seen it, Live Design is the show that we run every other Thursday between SolidWorks Live and Exploring 3D Experience Works. I'm going to see if we can't find some place to talk about 3D textures in that schedule. I think that'd be a good thing. Let's look at this next feature. Now, it's interesting here. You have a feature on here that I think I have told every SolidWorks user, don't put on your parts, and that is 3D threads. Tell me about the combination of Hole Wizard and thread here.
Yeah, so we're all familiar with Hole Wizard. It's a really handy tool for putting in, the correct tap drill size if you're going to send your parts out to a machine shop or something like that. Great for detailing. Tells you, snap a detailed call out to it. Boom, there's your hole size. You go back, change the hole size. Boom, your note updates with it. It's a beautiful tool. It's a great tool. Love it. The thread tool. Anyone who downloads fasteners from McMasterCar.com knows that there's no better way to absolutely crush your SolidWorks assembly than to have a bunch of fasteners with threads on it. So what do? We go in and immediately suppress that feature so that it doesn't just destroy our computer's performance. Well, here, if you actually hit the drop-down arrow just to the right of the Hole Wizard command, there's actually a thread call-out tool or a thread design tool in there. It is really good. I've been super impressed with printing. We don't touch any of the offsets or anything like that. We literally use the tool, print directly to it. Fasteners go in every time. If there's an accuracy issue, it's generally something to do with the machine, not to do with the design. The thread tool is really handy. You will get a warning message the first time you use it that says warning, like this is going to essentially destroy your performance if you use it. ignore that warning, but I will say this is the last thing you want to do on your model. You want to get everything else done, and at the very bottom of your tree, you want to go and put these in, because you will take a performance hit. So you want to put it in a place that's easy to roll back and suppress if you have to make engineering changes.
Yeah, Mark Peterson recently on Live Design did a great example where he modeled basically a monitor stand that went above his webcam, and he had to model some threads in there. He gives a great step-by-step tutorial on how to use this. So I encourage you, go back, watch Mark Peterson in Live Design where he models basically the portable monitor stand. Really shows how to use the thread tool for 3D design. One of the things I like here, Paul, that you've talked about and you've shared with me off camera is you use that hole wizard, because not only is it that tap drill diameter, which basically automatically tells the thread tool what size thread to use, but you've also mentioned sharing the model with somebody on the shop floor. They can hover over it, they get the tool tip, and it tells them what size fastener they need.
Yep. Let SolidWorks do the thinking for you. You know, you can draw a sketch, you can extrude, cut a hole, but why not just click a button and just let SolidWorks do all the thinking? I'm a big fan of work smarter, not harder.
Yep. So, Paul, one of the things I think a lot of people know, when you buy a 3D printer, you get really capable software to help you slice it and size it and all that stuff. But I know you want to give a quick shout out to the print preview tool inside of SolidWorks. Just really quickly, can you explain why this would be important for people using this?
So what's really handy here is not only are a lot of the consumer desktop printers on here, but a lot of the industrial printers are on here too. And their platform sizes are accurate. So if you're designing a part and you're like, I wonder if this will fit on a MJF 4200, instead of going out and trying to figure out what size the platform is, or calling me and asking me what the platform size is, which, don't get me wrong, I love to talk to my customers, but sometimes it's, 1 o'clock in the morning and you just need to answer right now. You can go in here and actually find the HP Jet Fusion 4200 and see, does my part fit, or am I going to need to put glue joints in? Am I going to need to plan on orienting it differently? So this is a really handy tool, just so that if you know what type of printer you're going to be running your parts on, and reach out to your additive manufacturing partner. I have customers reach out to me all the time. I go, oh, we're going to run it on this, we're going to run it on that, and then that way they can come back in here and kind of see how their parts are going to build. There's also a cool tool in here that kind of visualizes what your layer lines are going to look like. So like, for example, MJF, it's 3,000 layers, which is what this is set to right here. So it's super fine layer lines. Like, a lot of times you can't even see them in these parts. But FDM, it's 10,000 or maybe even 13,000 layers, which are going to be very aggressive and heavy layers. So you might be trying to minimize the appearance of layer lines on certain surfaces. This can be a great way to figure out how to work with your additive manufacturer on orienting your part to try and get the surface finishes you're looking for on your Class A surface, by sacrificing the surface finishes maybe on the B side of your part that no one's ever going to see.
Very cool. There's a great question we're going to get to in a little bit. Dallas Salad, we're going to talk about the thread tool in a little more detail here in a little bit. I want to quickly talk about designing some of these parts for your MJF process. We're going to look at a couple examples, and we're going to actually open up one of your designs. Mainly, there's like a question in here I kind of want to get to. Talk a little bit. So this is a part you designed for MJF. I can tell by looking at it, it's a bit of a fixture. Maybe explain what the part does here.
Yeah, so this is an assembly fixture. This gets bolted into a machine, and then there's a left hand and a right hand, so they'd be sitting on the machine pretty much like how you see them right here. And then you can see how the customer, the end part, the part that's actually being manufactured here, gets loaded inside of it. And what happens is a swing clamp comes down and pneumatically locks these into position, and there's an operator sitting there putting these metal clips in. If, let's say, the operator has a bad day, or maybe they forget and they don't put one of these clips in, and it makes it all the way out to the automotive plant, you've never heard anyone scream like you've heard someone when they call up and say, you just shipped us a part missing a clip and now our line is stalled, and there'll be a bill in the mail for you. So have fun with that. So what we have is these kind of slots that you see here. We actually have proximity sensors that go through those slots, and those detect the metal clips. So if the operator forgets to put a clip in one of these stations and they hit cycle finish, the machine will go, I see all the clips, or, oh, wait, this clip is missing. And then in some cases, it'll just say, hey, operator, put a clip in here, and then it'll unlock it and let them take the parts out. Or you might have a supervisor who says, hey, If a machine faults, there's a keyed reset. So the operator has to actually go get their supervisor and say, hey, I missed a clip, and then I need you to unlock the parts. And that could be a tool for management to make sure that, hey, we're holding people accountable if they're making mistakes. So, but yeah, it's essentially an assembly fixture.
Yeah, I mean, one of the things here that I want the viewers at home to look at, imagine trying to machine that part. Like, how unbelievably expensive would that be? Yes, you could do it. I want to keep moving here, though, Paul. One of my first questions that jumps into my mind is, this material, is it abrasive? Is it going to scratch these parts?
Yeah, so the parts that you see right here are interior automotive parts. You'll never, not interior to the car, but interior to the body of the car. You'll never see them. So there's no Class A finish requirements. But, I mean, let's say like the next slide we're going to look at, maybe you're assembling a chrome door handle. Well, this nylon would scratch chrome. It would scratch paint. It would scratch mold and color. So what we do is we also print with a 95A durometer TPU rubber on the MJF machine. So we'll take and we'll print the shell of the nest or the structure of the nest out of nylon for strength and rigidity, but we'll print inserts out of the TPU rubber, which are Class A safe, and they will not scratch your part. So you get the strength of the nylon, but you get the Class A safe soft touch of the TPU. So it's really the best of both worlds. And so there you go. You can see the customer's part sitting in that nest, and that chrome finish won't be scratched.
And you had mentioned earlier, one of the really unique things is mixing all of these technologies. So you have 3D printed parts. And when we look at the bottom of this, you've actually got pressed in threads.
Yep.
So you had mentioned this part's changed on and off the machine often. That's why you, instead of printing these threads, you use explain why you use the pressed in threads as opposed to the printed threads here.
It's all about duty cycle. So if you have a metal fastener going into a plastic hole with threads in it, over time, no matter how careful you are, you will wear those threads out. So if every shift you're changing out parts, instead of printing in the threads, you want to do either a heat set insert, a helicoil, a key insert, essentially a metal thread inside of your plastic part. And so this right here, you do not have to worry about those threads wearing out. Those brass inserts will last a very long time. So here it's not a strength issue, it's a wear issue.
All right. Well, Paul, I want to get into something fun. When I spoke to you, you said, well, I happen to be working on one of these projects right now. So forgive me as you're going to see me looking around, maybe not right at the camera here. I've got a Solidworks screen over here off to my side, and we're going to take a look at one of your designs here. Paul, tell us a little bit about what we're doing with this design here.
So this is a pre-production hand assembly fixture. Basically, our customers in pre-production, they are building their automated assembly machines, but they are not built yet. But yet they owe the end OEM that these parts are being built for. They owe them parts so that they can start assembling their product. So what we have is a hand assembly fixture. So you've got that part right there. If you flip that up, so we're loading this component into position. Just like that, and then if you look down on top of that secondary handle, you'll see there's a pin in there, and we're actually driving that pin into place to retain that component that we just lined up with its home position. Yep, just like that. And the customer was running behind on schedule. They needed something super fast, and I actually have. Oh, I'm not on video right now, am I? Okay.
No, we can. We'll switch back over to you.
All right. So I have this actual fixture. I'm holding it right now. This literally came off the printer as me and Jeremy were doing rehearsals this morning. These parts were warm when they were handed to me. Basically, Saturday and Sunday, I designed everything. Monday, had a design review. Customer bought off on it. Tuesday night, we printed. Wednesday, we cooled. And this morning, they quickly unpacked and threw everything together as best they could and handed it to me so I could show you guys. So we started on this past Saturday, and I'm holding a finished fixture minus a swing clamp that McMaster decided not to ship us, minus that one component. This is ready to go for review. And the even funnier part is the customer doesn't have end parts yet. They're still building the injection molds. So we even printed the green part that you see in there. We printed that, and so we can kind of use that as a start point to say, yes, everything looks like it's going to work, hopefully the molded parts are somewhat close to CAD. So it doesn't always happen, but hopefully they are. And so then we can say, like, as soon as you get parts, you can be sitting there assembling these parts and getting them out to the end customer.
Yeah, I mean, like, let's think about this really quick a minute. Imagine trying to have all these components machined. Well, first of all, you'd have to design them completely differently.
Yes.
The lead time on getting parts machined right now, Paul, what do you think? If say you design this for subtractive, how long do you think that would take?
Well, originally this was going to have an aluminum base plate, and I can't get that aluminum base plate in for about 2.5 more weeks. So there's major backlogs with materials right now. Even just getting material is getting a little bit difficult. So, best case scenario, the machine shop we work with usually can get something like that done in a week if I pay them expedite fees. But 2 weeks is pretty normal to get parts done out of aluminum.
All right. I want to take a look at one of these parts here in your design. I mean, I could look at any one of these parts. I love looking at people's designs right here. So when I look at this part, the first thing I go, if you brought this to a machinist, his head would explode.
Yes.
So what's interesting here is you told me you don't have to think about that when you're designing this way, right?
Nope. Take every rule you've ever learned about machine design for CNC or design for fabrication or design for injection molding, throw them out the window. There is a set of rules for doing design for additive, but it's a much shorter list of rules. So like, for example, that threaded hole that you see right there on the right, we've talked about using the hole wizard and we talked about using the thread command, but what I didn't tell you is you can see there's a big chamfer on that side right there. And if you're doing a 1/4-20 or smaller, I throw a 25 thousandths chamfer on there. And if I'm doing a 1/4-20 or bigger, I'll throw a 50 thou chamfer on there. And that's from me being a machinist back in the day. If I was going to tap a hole, I would always run a chamfer operation to put a chamfer for my tap to lead in so that I would have less of a risk of breaking a tap. But also when you go to run your fastener in there, it's just a smoother transition. I do the same thing here. We put a chamfer on there and it just gives a really nice lead in for putting that fastener on, helps prevent cross threading.
One of the other things I noticed, I want to talk about this thread tool. We're over on time. We're probably going to go just a few more minutes here to everybody watching. I think this has been really good and there's some cool stuff here. When you use this thread tool, one of the things I noticed is you sent me all this video of you modeling this part up, but I actually thought it'd just be cool to go into here and take a look at this. One of the things you do is I noticed the threads don't start at this face and end at this face. That you make sure that the thread goes beyond the extent of the material that you're cutting it through.
Yep. Yeah, it's really embarrassing the first time you do this and you go to thread a fastener in and it doesn't thread in and you look and you realize you were short by 15 thousandths for the thread breaking all the way through it. You look really dumb standing in front of your customer. So ever since I made that mistake, I run the threads 100 thou through either side. And that way I absolutely know there's no way that I'm going to have a too short of threads and I'm not going to be able to get stuff to go together.
So I want to quickly point out here, one of the things, because you used the hole wizard hole, you were able to locate all your holes early on in the design. You got the ability to hover over them, see what they were. One of the other things that's interesting is when you create the thread tool on a part or on a hole that's already defined, I noticed here, it looks like it would have automatically grabbed the correct tap size thread right there. So it's going to save you a little bit of time, right?
Yep, absolutely.
Now, Paul, there's a question in chat on YouTube. It came from Dallas Salad. He asked the question a ways back about, can you scale within the thread tool to account for shrinkage? I always have to chase all my threads. Now, I imagine this is something that differs per manufacturing process, right? Like FDM, that material kind of has some tolerance to it. Talk about how you use this in MJF. Do you have to do this? Yeah.
So, I would say it's very machine dependent. If we're printing threads on FDM, I actually don't print any threads under 1/2 inch on FDM because the resolution just isn't there to do finer threads, in my opinion and experience. SLA is a little bit better, but I wouldn't probably go below 3/8 on an SLA. And I would plan on chasing both SLA and FDM threads no matter what you do. MJF, we've had instances where stuff will print a little bit out of round and things like that, but those are pretty few and far between. Generally speaking, with MJF, the threads are good to go directly off the machine. We don't ever really chase them. And honestly, even if they're a little bit tight, you run that metal fastener in there once or twice, and it'll open them right up. But that's pretty rare. Stuff usually comes out pretty good on the MJF machine as far as threads go. We don't do any kind of scaling or offsets in SolidWorks. We print directly to the threads that the SolidWorks thread wizard spits out.
So really quickly, I want to go in here. So you get these parts done. You said you did these a couple nights. You even sent me the GoPro footage of this thing running overnight. So you guys track everything that you print. Something is always monitoring it. So how long did it take to maybe print these parts?
Yeah, so this is from Tuesday night, and if you look across the kind of the upper edge of the build volume, you can see 3 honeycomb parts sitting back there. That is actually these components here, here, and here. So this was only a half full build because it was such a rush to try and get it ready for today. So about I think it was 8 or 9 inches, and it ran for I think 9 hours. And then we cooled it, so that would have been Tuesday night. Then yesterday, Wednesday, we cooled it for about 12 hours. And then this morning, if you can flip to the next video, if you have it queued up, you can actually see Wes. This is literally this morning he was unpacking this build. So this was at like 9 a.m. Eastern this morning. And so he's going through vacuuming up all that extra powder that we're going to use on the next build. And here in a second, he's going to start pulling out the pieces that make up this fixture once he gets down to the bottom of the build.
Very cool. One of the things you mentioned, Paul, is the cooling period. And you explained to me when we spoke earlier that one of the interesting things about MJF is temperature. It gets so hot that you leave it in there to basically you got to let it like temper to keep it from warping, like all the powder. Explain that.
Yeah, so when you're printing, you're up north of 300 and probably 90 degrees Fahrenheit inside that machine, and you're putting a lot of heat into these parts. And if you were to just print them and pull them out of the machine and just unpack them immediately, first off, you'd need fire-resistant gloves because you're going to burn your hands badly. But then your parts are going to warp and twist and move all over the place. They have to cool at a slow rate, and that's what this machine does. So this is a separate piece of equipment from the printer. This is a standalone piece of equipment. When you buy an MJF machine, this is part of the package that comes with it. And essentially, these build carts that Wes is unpacking, you draw a vacuum at the top, and it slowly creates fissures through the cake, as we call it, that the parts are inside of, and allows the heat to come out of the cake slowly over time. And that powder acts like a cooling fixture. So if you've ever done injection molding and you've got a part that has a heavy walled region and your part wants to warp or twist on you, a lot of times when parts come out of an injection mold press, especially big parts, they might actually lock them in a cooling fixture so that they don't warp and lose their accuracy. You can think of this powder as our cooling fixture.
Well, this is really good, Paul. We've gone a little bit over. I want to thank you so much for coming out here today. I'm going to do what nobody wants. I'm going to jump around in this slide because there were a lot of questions we didn't get to here today. So I want to,
if you have time, I have time.
I just want to respect our audience's time. So if people have any questions for you, how can they reach out to you? I'm trying to get back to this specific slide in this in our presentation here.
It's all good. So yeah, you can email me directly. So it's Paul at forerunner3d.com. So PAUL at FORERUNNER, the number 3 and the letter D.com. You can Google Forerunner 3D. Forerunner 3D printing will pop right up, and there's my contact info on there too, and our you can request a quote or hit our sales account up. I'm pretty prolific on LinkedIn. Love to post content on LinkedIn, post a lot of videos, a lot of testing and R&D that we do here. So if you look up Paul DeWys on LinkedIn, as far as I know, I'm the only one. So that's PAULDEWYS. Feel free to shoot me a LinkedIn contact. Even if we've never met, I'm always happy to connect with people, and I'm happy to talk with people on there as well.
And Paul, you've given presentations at 3D Experience Worlds 2 different years on a very similar topic to this. So that content's actually available. We did a SolidWorks live stream from your broadcast. I think it was 2 years ago we broadcast your presentation there. So definitely more to see there. Paul, again, I want to thank you so much for taking time out of your day and your week, sharing your design with us that you worked on and the final parts that you did.
Hey, no problem, Jeremy. I appreciate the opportunity. And like I said, big SolidWorks fanboy, been using it for a long time. So just thrilled to have the opportunity to talk with you today.
All right. We're going to quickly close out here. I want to thank everybody for joining us online today, whether you were on YouTube, LinkedIn, Facebook, or Instagram. Hopefully we answered your questions. If we didn't, keep them coming in the comments below. Make sure you stay tuned, at least on our YouTube channel. Next Thursday on April 29th, we are going to have Exploring 3D Experience Works back. That's with John and Gian, and they're going to be designing an electric winch using 3D Creator, 3D Sculptor, and 3D Sheet Metal Creator, all on the 3D Experience platform. That's going to be really exciting. They're going to be using purely cloud-based or web-based apps all through their browser. So that's going to be pretty cool. And remember, we're always putting out content every Thursday on YouTube, even if we're not on all the other channels. So make sure you're subscribed and you hit that bell notification icon so you know when we go live. Our next SolidWorks Live is going to be on May 13th, where we're going to be spending time with Jason Poole, formerly of Orange County Choppers, and he's going to be going over some of his design workflows. Now, this is going to be different than what we've looked at in the past at 3D Experience World. He's going to be showing us how he's been using the 3D Experience platform to really change the way he designs things. I want to thank everybody for joining us here today, and I want to give a special shout out to my guest, Paul, for staying on a little extra. I hope everybody enjoyed this content, and we'll see you in the next one.